In this lab, we were to estimate the mass of a black hole given the hole's position and the mass and position data of a star that was orbiting that black hole. I used the principles in Newton's second law to calculate the mass. My estimate of the mass of the black hole turned out to be 3.58 times 10 to the 31st kilograms, approximately 18 times the mass of the Sun. We were to estimate the mass by analyzing the star's motion in Python to calculate the net force on the star for all points in the dataset. We assumed the net force on the star was solely due to a black hole, given at this location. To make my Python graphic module, some initial conditions had to be inputted in addition to the black hole position. The position data of the star was given as the star data file, but this only had x and y coordinates. In Python, I set the time step to be 86,400 seconds, or 1 day. Finally, the mass of the star was 5.3 times 10 to the 27th kilograms. My origin was 0 meters in all axes directions. Finally, at the end of my Python code, I adjusted my areal scale to be 7 times 10 to the negative 14th. Also, for my rate was 150. I manipulated these so my module ran at an appropriate speed, and so my arrows were of a suitable length for my drawing. Here we see the Python module. The black hole is the white donut shape in the middle of the screen. Notice that as the star gets closer to the hole, the forces, represented by the arrows, increase significantly. This is due to the increasingly small distance between them. This is backed up by the formula F equals gmm over d squared. These algebraic statements are the statements written in my code. Note that these are not equal to each other, but calculated at each point. We are using Newton's second law, the principle that the F net is the change in momentum over change in time. This is what we use to calculate all the values that you see on the screen here. This critical statement is seen in the first line. They all change constantly throughout the entire orbit. The what-if question asks if it is possible to find a value for the mass of a new black hole that is different from the mass of the original one if it is placed in the same location and the star's motion does not change. The answer is that there is no new mass of the black hole, if only the force on the star is the force from the black hole. It would be the same black hole. To calculate the mass of the black hole, we could do a few things. We could either calculate the mass of the black hole by hand, or have Python do all the hard work. I chose Python. I inputted the code to follow the following expression. The mass of the black hole is equal to the net force times r squared, divided by the gravitational constant times the mass of the star. R is the quantity of the star's motion minus the hole's position. In the diagram here, this is seen as the distance d. Overall, I'm quite happy with my module. It seems to successfully predict the motion of the star orbiting the black hole. Before making this video, we were instructed to test our mass value for accuracy on WebAssign. Upon submitting my value, WebAssign said that I was correct, making my answer seemingly valid.